This is Beijing Daxing Airport. They're one of the largest and most complex airports ever built in human history. And what is hard to believe is that this colossal project was completed in less than 4 years. China, the king of projects whose scale far exceeds conventional standards, transformed a vacant area south of Beijing into an aviation hub capable of serving hundreds of thousands of passengers every day. Building big is difficult, but building something that is fast, massive, precise, and able to operate reliably for decades is the real challenge. In today's video, join Mandarin Tech as we dive deep into the bold ideas behind Beijing Daxing and how it is reshaping global aviation. The emergence of Beijing Daxing International Airport was not merely an ambitious choice, but an inevitable consequence of infrastructure pressure in China's capital. For many years, Beijing Capital International Airport, the nation's primary aviation gateway, had been operating well beyond its design capacity. Despite being expanded at a cost of billions of US dollars ahead of the Summer Olympics, the airport once again reached its capacity ceiling after only a few years. When annual passenger traffic surpassed the 100 million mark, Beijing faced a critical dilemma. Without the construction of a new aviation hub, this congestion would constrain economic growth, disrupt national transportation networks, and directly undermine the political role of the capital. In this context, Daxing was planned as a strategic pressure release valve, not only to relieve the existing airport, but also to ensure that Beijing could continue to function smoothly for decades to come. To bring this goal to life, Chinese architects and engineers, together with international teams, went through a design process that lasted many years, during which more than 200,000 technical drawings were drafted and refined. The subsequent construction phase then proceeded continuously for 54 months, mobilizing hundreds of thousands of workers and transforming an empty site into one of the largest aviation hubs ever built. Located approximately 46 kilometers south of central Beijing, in an area bordering Hebei province, Beijing Daxing International Airport was planned from the outset, according to the standards and structural logic of a new generation airport. The entire airport covers an area of more than 45 square kilometers, large enough to integrate runways, terminal buildings, technical zones, logistics facilities, and safety buffer areas within a single unified site. The central terminal has a total floor area of approximately 700,000 square meters, organized as a continuous space rather than separated blocks, in order to minimize internal walking distances. At full operational capacity, the airport is configured with 6 parallel runways, enabling the simultaneous handling of multiple takeoff and landing flows at high density. These figures reflect not only sheer scale, but also demonstrate how China approaches an airport as a complete infrastructure ecosystem, rather than as a standalone transportation facility. Foundation construction is a quiet yet decisive phase of the entire project. Across a site spanning dozens of square kilometers, the construction area was divided into multiple zones to allow parallel operations, ranging from weak soil treatment to elevation leveling. Heavy machinery operated continuously, combined with GPS surveying technology and sensors to precisely control each foundation layer. The site was subdivided into numerous control points to monitor settlement and compaction in real time. At peak periods, tens of thousands of workers were engaged simultaneously, gradually completing the project's technical foundation. It was this rigorous control from the foundation stage that ensured the entire superstructure above could be executed in a stable, coordinated, and durable manner throughout its operational lifespan. Beyond its sheer scale, Beijing Daxing Airport is also shaped by a design philosophy intended to leave a strong first impression, while at the same time solving the challenge of moving tens to hundreds of millions of passengers smoothly each year. To address this problem, Chinese architects and engineers turned to a classic precedent in the history of urban transportation, Grand Central Terminal in New York. More than a century ago, this station handled hundreds of thousands of people every day, not through dense signage or forced control, but through intelligent spatial organization. A vast central hall, unobstructed sightlines, ramps instead of stairs, and clearly layered circulation flows. As a result, people could intuitively find their way without complex guidance. Beijing Daxing does not replicate the form of Grand Central, but inherits this core idea and applies it to an aviation-scale context. Instead of lining up dozens of departure gates along long corridors, the terminal is organized around a central core from which 5 finger-like concourses extend outward. This layout shortens the distance from the center to the farthest gate to about 600 meters, creating a continuous, orderly, and efficient flow of movement for millions of passengers each year. The next challenge was to cover an enormous space while maintaining visual and spatial continuity. The ambition to create a vast roof without supporting columns forced the engineers of Beijing Daxing to seek solutions beyond conventional structural systems. Instead of starting with entirely new technologies, they looked to Poljud Stadium, a structure built in 1979, where a three-dimensional space frame had been used to cover the entire grandstand without obstructing sightlines. Steel members were connected into triangular modules, allowing loads to be distributed in multiple directions, increasing structural stability while reducing material use. This principle became the conceptual foundation for the roof design of Beijing Daxing. Turning Daxing's massive space frame roof into reality presented a construction challenge on an unprecedented scale. Rather than assembling the entire roof at height, a method involving significant risk and difficult-to-control tolerances, the engineers adopted a segmented construction strategy. First, 8 primary load-bearing columns, which together form the entire support system of the roof, were erected with absolute precision. These columns serve as the only anchoring points carrying the full load of the steel roof above. Instead of assembling the entire roof structure at height, the construction process was carried out progressively from the ground upward under strict control. Roof components and cladding panels were prefabricated on the ground, then lifted into place using aerial work platforms, cranes, and specialized equipment. At elevation, workers operated directly along the roof edges to align and secure each metal and curved glass panel according to the precise geometry of the design. Installation proceeded sequentially in strips, ensuring accuracy while significantly reducing safety risks. When completed, the roof, weighing more than 57,000 tons, resembles a floating steel forest suspended above the terminal. Beneath it lies an acoustic ceiling for noise reduction, while above are more than 8,000 daylighting glass panels and 40,000 aluminum cladding panels forming the exterior surface. Just 111 days before operations began, the entire roof envelope was fully installed, marking one of the most impressive construction milestones of the project. Although the planning process lasted many years, Beijing Daxing International Airport was completed in a record time of 3 years and 9 months. Before its opening, the airport entered a large-scale operational trial phase with more than 51,000 volunteers simulating real passenger flows. The results showed that travel time from the central hub to the farthest gate was under 6 minutes, exceeding initial expectations. In parallel, the technical systems were comprehensively reviewed. 7,100 intelligent LED lights were tested. Emergency scenarios were rigorously rehearsed, and nearly 20 kilometers of underground technical tunnels were put into trial operation to ensure stable infrastructure before the airport officially opened. Daxing goes far beyond the role of a conventional airport. The project demonstrates that limits once considered impossible in construction can be overcome through technology, organization, and determination. At the same time, it has become a powerful engine of economic development for the entire Beijing-Tianjin-Hebei corridor. The image of Daxing's massive starfish-shaped terminal has spread across international media, telling a story of modernity, innovation, and exceptional capability. On a global scale, Daxing helps reshape the map of international aviation hubs. As China stands as one of the world's largest centers of production and consumption, A mega airport capable of stable operation at an extremely large scale has a direct impact on global supply chains. The airport thus functions as both an economic and strategic instrument, influencing trade, high-speed logistics, and China's position in global connectivity in the 21st century. From the strategic role of Daxing in reshaping the global aviation network, the next infrastructure story takes us to the Middle East, where King Fahd Airport was built in a very different context, yet reflects an equally ambitious vision of scale and connectivity. King Fahd International Airport is considered one of the most exceptional aviation infrastructure complexes in the world, not because of traffic density, but because of its unprecedented scale and planning mindset. With an area of more than 786 square kilometers, larger than many mid-sized cities, King Fahd was designed as an aviation mega-campus in the middle of the Dammam Desert, where every zone, from the passenger terminal, cargo area, and maintenance center, to the dedicated aviation facilities of Saudi Aramco Aviation, operates as an independent unit, yet remains tightly interconnected. Two parallel runways, each more than 13,100 feet long, enable stable handling of long-haul flights, while the expansive taxiway system minimizes intersections and enhances operational safety. From a strategic perspective, King Fahd is a clear testament to Saudi Arabia's effort to shift its economy away from dependence on oil, moving toward a model based on aviation, logistics, and commercial services. The project is positioned as a key piece of infrastructure for the entire Eastern Arabia region, connecting Dammam, Al-Khobar, Dhahran with the rest of the region and the world. Under the 2030 vision, the airport is planned to accommodate 120 million passengers per year, a figure expected to rise to 185 million by 2050. In terms of economic impact, King Fahd plays a vital role in supporting non-oil growth by promoting trade, business travel, and aviation services. The airport creates tens of thousands of direct and indirect jobs across sectors such as airline operations, ground services, transportation, supply chains, and engineering. Thanks to its strategic location and massive land area, King Fahd is viewed as a core infrastructure asset that helps Eastern Saudi Arabia maintain its development momentum, while strengthening the country's position as an increasingly important logistics hub in the region. The idea of building a large-scale airport in Eastern Saudi Arabia emerged in the late 1970s when air transport demand was rising across the Dammam-Dhahran area. The government chose a vast desert region northwest of Dammam, about 35 kilometers from the city center, because it offered enough land to develop an aviation infrastructure complex for decades to come. The total planned site area reached 776 square kilometers, making King Fahd the airport with the largest land area in the world. In the 1980s, construction teams began leveling the desert to create the foundation for the terminal, runways, and taxiways. The work focused on reshaping the terrain by flattening natural landforms and large sand dunes and reinforcing the surface to support the loads of a modern airport. Because this was a desert region, the biggest challenge was controlling drifting sand and ensuring ground stability before placing structural systems. All activities complied with the standards of the Saudi Arabian General Authority of Civil Aviation, Shirgaka, and the United Nations International Civil Aviation Organization, ICAO, for airport foundations in hot and dry environments. King Fahd was designed with two runways, each about 13,100 feet long, enough for wide-body aircraft to take off and land. The construction team laid the base layer of the runway and then covered it with a specialized asphalt concrete capable of withstanding temperatures of more than 120 degrees Fahrenheit in eastern Saudi Arabia. The two runways were built in parallel, allowing the airport to handle multiple flights at the same time and accommodate long-haul aircraft. From the late 1980s to the early 1990s, the terminal was built with the distinctive architecture of the Gulf region. The project included spacious halls, check-in areas, arrival and departure corridors, and technical facilities. At the same time, The air traffic control tower was constructed to oversee all flight movements across the airport's vast area. Supporting facilities such as the Royal Terminal and a dedicated terminal for Saudi Aramco Aviation were also built according to specialized operational standards. Once the main structures were in place, the electrical system, runway lighting, large-capacity air conditioning, ventilation, water supply, drainage, and aviation telecommunications were completed. All aviation equipment, such as radar, navigation systems, radio communications, and baggage handling were integrated according to international standards. GACA and international contractors worked together to ensure that the airport could operate under high temperatures and the harsh desert environment. By 1990, most of the airport's infrastructure had been completed. Highways were expanded to connect King Fahd with Dammam, Al-Khobar, and Dhahran, turning the airport into an important transportation hub for the eastern region. Supporting areas such as aircraft parking stands, cargo warehouses, maintenance centers, and auxiliary services continued to be added throughout the 1990s. The airport officially opened on November 28, 1999, and has since become the largest aviation gateway on the eastern coast of Saudi Arabia, serving more than 10 million passengers each year. After all the layers of engineering, structure, and operations, Beijing Daxing leaves behind a larger question about how modern infrastructure should be built. From design decisions inspired by history to structural and seismic solutions, and to the way people and technology are organized to operate together, everything shows that this airport was not created to overwhelm, but to function reliably, stably, and efficiently in the real world. And Beijing Daxing is just one of many examples of how the world is being reshaped by such silent mega projects. If you want to continue exploring the infrastructure, engineering, and technologies quietly powering our planet, don't forget to subscribe to Mandarin Tech, turn on notifications, and join us in the videos to come.